Well, we're back again with some more tube theory. As promised in part 3, I was going to talk about different ways to bias the tube. We're going to start out with what is known as fixed bias. And fixed bias means that the tube's not doing anything for itself. It's getting its bias from some other means. In the case of this first one that we're looking at, this is what you'll see quite a bit in late 40s, some late 30s, early 40s, late 40s, and on, where they take off a point on the center tap, a B plus of your B plus supply, your high voltage secondary. Normally the center tap would go to ground, but instead they'll put in a voltage divider resistor. It could be just a couple resistors, 3, 4, 5, whatever, how many different bias or negative voltages they want before they take it to ground. In this case we're running a couple resistors here. Our main concern is this R right here, because it's the nearest to the ground, and that's where we're taking off for a grid bias. RG has no current going through it, so whatever voltage that develops here will be what is at the grid. Grids don't, as long as they stay negative, never have any current going through them. So we establish, we figure out what we want for our operating point. So figure out what voltage that needs to be. In our design, we'll know how much current is going through the circuitry, meaning how much current goes out and is drawn by the radio, which will come back into the center tap. And then we can size this resistor accordingly by using Ohm's law. We know what voltage we want. We know the current that's going to be going through it. We just do a simple take the voltage divide by the current, gives us a resistor. We set a resistor here, and that'll give us whatever bias voltage we want. Now another means of doing it is in a lot older radios where you have a bias cell that goes to ground. They just basically, a bias cell is a battery that is hooked in where the positive goes to ground. Now some of these may have an RG here, may not. It all depends on the coupling circuit and how it's all hooked up. But in any case, you'll have the bias cell, and that's how you get your negative voltage. Now for those who deal with these, basically if they go dead or seem to be dead because they're old, a lot of times all you got to do is get some water added to them, and there's various techniques, and you can find them on the web. You can do a search for it, find them on YouTube, to get the liquid back in and get these things to come back to life. Now the thing is, you got to realize and remember one thing: generally no current ever goes through the grid. So if you revive these, and then let's say you check them with your digital voltmeter or whatever, and it's not showing like it should. Maybe you're supposed to have like a couple cells, and each one's say around 1 volt, 1.5 volts, and it should be like 3 volts for total. If it's not showing that, but it is showing a revived voltage, don't worry about it. It most likely will work. You got to realize, in order for that meter to work, in order to get anything to show up on that screen, it has to draw some current. So it's going to load these. These things were designed not really to put out much current at all. Very little, way down to microamps, because they're designed for biasing a tube which the grid has no current on. So they would actually be just fine being hooked in there. If you're getting like 7.7 volts or something with a digital voltmeter, try them. They'll probably work just fine for you. If not, you can put a resistor in here, and we'll get to that in a minute. Okay, another very common way of biasing is called self-biasing. And one of the most common ways of doing it some of the common ways anyway, is by putting a resistor in the cathode circuit. And this is called cathode bias. Now, you'll generally see these, and you'll see them with a bypass capacitor here. Bypass or decouplings, basically the names are interchangeable. The circuit will appear like this. You'll have a, it may, probably go to ground or something, but it's going to, and I have a capacitor across it hooked to the cathode. Now the whole idea of this is, when you put a resistor in here, this side will be negative, but this side will be positive. So it's actually pulling up the cathode to a positive charge on it in respect to the grid. Or in other words, the grid will be negative now with respect to the cathode. You have a complete circuit right here, and that's all it's doing. Whatever voltage drop is here will be the voltages on the cathode, and that'll be the bias voltage that you're going to be using. Now, how do you get this and figure it out? Well, it's pretty simple. You make use of your tube manual. You get an idea of what you're going to be running for a plate voltage here. You look up the tube manual, get the closest thing to the plate voltage you got. It'll give you plate current. No signal, plate current. Whatever goes through the plate has to go through the cathode. So plate current's fine to use for the cathode. Then you just simply use Ohm's law. You have already determined what voltage you want here for your grid. So you just use Ohm's law. So RK is your grid voltage, your operating point, no signal, divided by the plate current up here. And that'll give it. Now, that's fine for a triode. If this is like a pentode, you have to add in one other current, and that's the current that goes through the screen. If there was a screen in here like a tetrode, or a screen and a suppressor like a pentode, the screen also has current which comes from that cathode. So then you have to add the two, so it would be EC over IB plus IS, or I screen. But either way, just use Ohm's law, and that's how you get this size. What about this size? Well, the capacitor, bypass capacitor, basically what you're looking for is you want, in a rough sense, you want the signal to bypass. The whole reason why this is going to be here is when a signal comes in here, what does it do? We learned before by looking at some charts and stuff, whatever varying voltage that's going here is going to vary the plate current. Well, that's going to vary the cathode current, which is going to vary the voltage across here, which now is going to change and vary the no signal grid operating point, which is really going to start messing up your bias. So when I got a signal, I want it to go through here and not here. Well, the way I do that is I add this capacitor in here, but I set this resistance of this capacitor, which is also known as capacitive reactance, X sub C, to be a lot less than RK for the lowest frequency that this thing's going to operate at. And what that does is electricity takes the route of least resistance. So when the AC signal comes through, it's going to see this, but this is 10 times less, so it's going to take this route. Now, how you figure that? CK is 1 divided by 2 pi F X sub C. Basically, it's just rearranged formula for X sub C. X sub C equals 1 over 2 pi FC. And that's how you figure out this capacitor. One thing is, F is frequency. You're going to be looking at your lowest frequency, and it'll be in hertz. No megahertz, no kilohertz, no nothing, just hertz. And X sub C will always be in ohms. It will give you a value in farads, so you'll have to do the math on that to convert that to something that you can use. and a value that you can make use of and find in your drawer or order. Basically what this is an RC filter. And in the actuality, the way it works is what they call an RC time constant. When you got a capacitor and resistor, whether they're in parallel or they're in a series connection, basically you multiply the two values together and they'll give you what they call the RC constant, time constant. And what that means is how quickly does this capacitor discharge once this voltage is taken from it. And it's figured in seconds. R is in ohms, C is in, actually in microfarads, and time in seconds. But that's cathode biasing, and that's how that works. Now the next one is one you see in some radios that are newer, and there's two different styles, this style and this style. It's called grid leak. It was used considerably in TRF radios, especially on the detector tube, detector first audio tube, triode. Now, the way grid leak works is it's basically making use of that CGRC or RC time constant. And basically what happens is when you first fire up the radio and no signal's going through, bias is zero. Nothing's happening on that grid. As a signal comes through, it will actually start to charge. That's what the green path is. My capacitor. When the signal is in one direction. When the signal switches directions, it'll start a discharge path, which is the red. Which in turn, if you notice, we got negative here, which would make this negative, which keeps the grid negative. As it goes back the other way, it starts charging again, and then discharge. Same thing happens over here. Except we got them in parallel. This was series in parallel. The discharge path is between the capacitor and resistor. The charge path is the entire tube and this parallel network. And that's how they work. Now, in order for them to work, we need to have a decent time constant. So generally RG will be sized out from 1 up to 5 megs. Generally 1 to 3 megs, sometimes as high as 5 megs, to give a pretty decent time constant so that this capacitor will never discharge below a certain point. In other words, it's constantly keeping a pretty steady negative voltage potential at the grid, and that ends up being our operating point and our bias. One last one that's used tremendously with certain tubes and more newer radios, things like the 6SQ7 and I think the 6AT6, and there's a few others, is what is known as contact bias. And if you're not sure what 6SQ7 is, that's the dual triode or dual diode triode tube. It's the detector with the first audio. In these tubes that use contact bias, generally actually you can use contact bias with about any tube, but there are certain tubes that are specially designed for it, like the 6SQ7. And what they do is they actually move the grid actually fairly close to the cathode, closer than normal. And why they do that is, what contact bias is the cathode is a negative potential in the tube. So while it's got all these electrons, it's flowing through and everything, some of these electrons are going to make contact with the grid, and they're going to stay there. And what that ends up doing is making the grid look negative with respect to the cathode and everything else. So you end up, and that's what you want, the grid should always be negative. So you end up with a negative voltage there, or actually negative charge. Now, the way to make it work is you want to make absolutely sure that you can never have any type of current flow in there, and the way you do it is your RG, your standard grid resistor, you make it extremely large. Usually somewhere from 3 to 15 megohms is the standard size. That pretty well limits any potential of this grid going positive and keeping it pretty much negative, so that the contact bias will work. Now, contact bias is not a huge bias. It ranges between 1 and 1.5 volts max, but it works. Like I say, the 6SQ7 is one tube that uses it pretty much anytime you see it in any radio. So that's pretty much it on biasing methods. If you have any questions, leave them in the comments and I'll see what I can do to answer them. Really, there's not a whole much else to say about it. It's not really complicated to understand. On our next video, I've thought about this, but I think what I'll do is I'm going to pull out a schematic, because I want to stay in the realm of our voltage amplifiers for just a little bit longer. And I want to pull out a schematic or two and just kind of, let's look at the real world and see if we can pick out the parts and stuff of the circuits for a voltage amplifier, and try to understand some of the paths, current paths and stuff. So until next time, thanks for watching. That'll be it.